All right, let's go get started. Let me get the lights and whatnot adjusted. Okay, so before we get started, let's go through a few announcements. It feels like we haven't met in ages because of the holiday, but so I wanted to take a moment and make sure everybody's on point with some things. Okay, first off, I hope everybody is on the way to getting their manual. If you haven't already done so, you really need to start bringing it to class on a regular basis because we're going to start using it in class when we work on examples. We will be opening it today and we'll be referring to some sections and tabbing some sections and whatnot. So if you haven't ordered it, you really need to order it as soon as you can. If it's in the mail, no big deal. You aren't going to need it for homework for a little while. But one big thing is you really, when you get it, you need to start bringing it to class. I know it's clunky, I know it's big, but you do need to bring it to class. How many has theirs? I'm just curious. Okay. Now, did everybody bring it to class? Okay, you have officially earned one of these.
We haven't used it yet, so I
We will. Seriously, we're gonna start referring to it in class quite a bit. So, I mean, we'll start off easy, but like down the line when we get to like column design and whatnot, I mean, you will have to have it in order to do the stuff we do in class. Like you'll just have to have it. Okay, next time. But see, I put it in big red bold letters, so you can't forget. All right, your homework's due on Friday. So, anybody have any questions? I figured I'd open the floor to see if anybody has any questions about it. Yes, sir.
Yeah, the first building problem, I couldn't distinguish if it was a wind exposure B or C.
Well, that's a good question. So the question was whether or not it's a wind exposure B or a wind exposure C. If you read the first sentence, I'm going to read it out, and this is all I'll say. You've been tasked with assessing the lateral stability of a new commercial office building in the rural community of Marion, Kentucky. Okay? Now, if you go to Google and look up Marion, Kentucky, I think it might answer your question.
I did actually do that, and I still
Well, I don't want to say Marion, Kentucky's in the middle of nowhere, but it is a pretty rural community. It's not a city. You see what I mean?
So
There you go.
C does not mean flat land because that's
The difference between exposure category B and exposure category C is exposure category B is sort of in the middle of a city where you have a number of buildings that are blocking the exposure of wind. So if we were building a new commercial office building in downtown Huntington, that would be exposure category B because there's a bunch of other buildings there that are going to influence, the aspects of wind. But if we were building the same structure in, let's say, Milton, that'd be a different story because it's a little more open. Do you see what I mean? It's not a matter of flat. It's a matter of how open the area is to different barriers. Does that make sense?
the coordinates are like in the middle of the city there. So
Yeah, but if I understand what you're saying there, but if you look at that city, it's not very big. It's pretty small. Yes, sir. Hold on. Shh, I can't hear him. Can't hear him. Yes, sir. What's that? I don't think so because read the first paragraph. It says geotechnical investigations have yielded a soil profile of site class C. That's a different animal altogether. The soil profile is literally the geotechnical properties of the fill right there at the site. The exposure category has nothing to do with that. Soil properties and exposure categories are completely independent. But does that answer your question? Now, it just so happens that, yeah, they're both going to be a letter C, but that doesn't mean that they mean the same thing. Everybody good? Okay. So the technical conference is next Thursday. Of course, I'm sure they're always going to want volunteers. So I know they developed a big volunteer list last night. So contact Logan Stackstow if you're still interested. I'm sure more hands on deck is always a good thing. Again, a chance to rub elbows with potential employers. I'm not 100% if this came out or got out to the students, but it should have. There's a West Virginia Society of Professional Engineers scholarship where the submission deadline is January 20th, which is on Friday. I don't know if you all got an email from Dawn about that, did you?
Yeah, it was last semester that.
Did you get one recently?
I'm talking about November. We got one.
Okay, all right. I will check with Dawn about that, but yeah, the submission deadline's on Friday. I'll be honest, I don't know the extent to how much work goes into the submission. I know there were some emails passed around some of the faculty over the weekend, and that's the last I heard of it. So I just figured I'd mention it. I didn't know if you had gotten it or not, so but I'll ask. Okay. All right. Today we're actually going to start talking about steel. I mean, this first week or so has really been about just talking about some of the basic load provisions, but it's also, I wanted to talk about a lot of that stuff first to give you all time for the manual to come in. So again, if you haven't ordered it, you need to get that and start bringing it to class. I do want to start to get into some things with the manual. If you don't have one with you, first off, you'll want to start bringing it to class, but you can, I guess, peer over the shoulder, sit next to somebody who does, and we can find some things to go through it. One thing I'll point out, so I did sort of, let's see, did it? I had this plugged up. Let's see. Okay. Real quick, all right, everybody, settle down. All right, real quick, I did sort of soft pedal some of the stuff near the end of the last lecture, and I want to go back to some of that. Last lecture, we ended on seismic effects, and we did a big example looking at seismic load. I did, and this was the example that we did. I did sort of, I guess, really quickly mention some of the other loading aspects that we need to deal with, which are dead live and snow. And I've got a few slides that summarize, here's the basics on dead loads, and here's some common values that we would use. Here's some basics on live loads, some info on what, various live loads look like, and going over live load reduction, and then also talking about snow. I went through this very quickly because in concrete design, we spent a fair amount of time delving into this with significant detail. So if you've already had concrete design, you've already seen this. And if you're in it now, well, we just went through it very significantly. So I figured I'll just sort of go over it, for the folks that have already seen it or saw it a year ago. But, I'm not really in this course going to test you on things that you've either A, already seen, or B, dealing with in another class. I just wanted to expose you to it, and then we'll move on. And last, I know we've talked about FD, the idea that your factored resistances need to be greater than or equal to your factored loads, and we discussed some of our fundamental load combinations in concrete as well. So with that, I wanted to sort of say, all right, let's get into the manual. So today, what I want to talk about are some basic provisions associated with the steel manual. I want to just go over some basic stuff, where to find some very pedigree values and basic information, and just hopefully try and maybe instill a little bit of relaxation about the manual. I know sometimes the first time you see this thing, you think it's massive. You're like, God, I have to memorize all of this. No, you don't. It's really about understanding how to use it. You don't have to memorize all of it or remember where every single thing is. Usually it's documents like this are laid out pretty well, and it's more about being able to find what you need. And hopefully we'll go through some of that today. So first off, a little bit about what this is and the organization that produces it. So this document is produced by AISC, which is the American Institute of Steel Construction. And by and large, they're the premier organization, not just in America, but I'd argue really on the planet, that publishes technical information related to the design and detailing of steel structures. And you'll find when you start getting into practice that there are a lot of organizations that are built around these specific interests. So for instance, ACI, the American Concrete Institute, their job is to publish documents and specifications relating to the detailing of concrete structures. And then there's the, AWS, the American Wood Society for Timber, or AWC, sorry, American Wood Council. for timber and whatnot. And there are various trade organizations that do this. A lot of times it's because of their folks that have a stake in this, folks that have an interest in this. So a lot of the folks that fund and back AISC are a lot of steel mills and fabricators, because to them, this kind of matters. Engineers having a good understanding of how steel works will lead engineers maybe to use steel more. So there's a lot of that happens in the world of civil engineering. Don't take that to mean anything negative. This is a good thing, that the actual experts in the field, the folks that are producing steel structure, and the folks at Lincoln Electric that are designing weld electrodes and whatnot, they're the ones who are telling you this is how you need to design some of these elements. So that's really all in all a pretty good thing. Now, you go to AISC's website, there's hosts of resources beyond this, but by and large, this is one of, if not the most popular resource that AISC publishes, and that's the Steel Construction Manual. Now, to give you kind of an idea of how this document is laid out, it essentially consists of three main resources. So the first, the way I look at this, the first resource is all the dimensions and material related values. So if you start thumbing through the manual and you start going through the first few pages of the manual, you'll start to get an idea of what I mean by dimensions and details. So you'll notice, you'll see tables of like W shapes and angles and things like that. And the idea is that if I'm, doing some design work and I'm using, let's say, a W14 by 90, I need to know what the area is. I need to know what the moment of inertia is. I need to know what the flange width is, and etc. That's where you get that, is here in this first part. Now, I'm going to skip ahead a little bit. The end of the document, which is this area back here, you can kind of tell where you're going to be. If you notice, some of the pages have this kind of gray lining. Everybody see that? This is where the actual code and specifications are for the document. So this is the part of the document back here, somewhere sort of in this region, that will tell you, if I'm designing a bolted connection, this is the equation that I'm going to use. Or, if I'm designing a column, this is the model that I use to determine that column's capacity, and et cetera. So that's going to be the actual the location for all the equations that we use throughout the semester. Now, the grand middle part, or the large part of the book, this part that takes up most of the middle, is really what you're spending your money on, and these are the design aids. You'll know you're in the right section when you see tables that look something like this. There'll be tables with a lot of green and blue numbers. I'm sure you can probably just start thumbing through the manual and find what I'm talking about. And there's design aids for all sorts of different things, for available strength for axial compression, and the beam charts, and ZX tables, and stuff that we'll investigate throughout the semester. I do want to sort of institute Rule 1 right now for us. If you recall, we have two design philosophies that we can use in structural design. One of them is allowable strength design, which is just taking the values and dividing them by a blanket factor of safety. And the other is LRFD, factoring the loads and factoring the resistances. In this course, we're going to use LRFD. What that means is whenever you look up any tables like this and you see green and blue numbers, we're going to use the blue numbers, okay? So, or the numbers that aren't shaded, okay? So, does that sound good? So from here on out, that's just sort of going to be rule number 1. It's nothing to say that using the green numbers, that's not saying that they're incorrect. It's just you're using different load factors and different safety factors. And by and large, I find it easier during a steel design course to just pick one and go with it. Some professors actually make the students go through both, and I just think it just becomes, just for me, I think it becomes kind of a waste of time, but that's just me. So we're just going to pick one and go with it. We're going to go with the blue numbers. Okay. Now, couple things that I mentioned at the beginning. One of the things I mentioned was in regards to these little stars that I would have in my PowerPoints periodically. Those stars refer to sections in the manual that you're going to want to tab. Okay, so let's actually navigate to this page. So page 2-10. Now, first off, the 2 refers to the section of the manual that you're in. So if you notice, when you open your manual, it's kind of hard to see on mine, but maybe, let me see yours. Yours, the manual's new and doesn't have. All right, see these little gold, these black and gold inlets that you see right here? So this first black and gold inlet right here would be section 1, and it says DIM for dimensions. Does everybody who has a manual see that? So section 2 says GEN, that stands for general. Section 3 has beam on it. Section 4 has COL for columns. Everybody see that? Okay, all right. So we're going to go to section 2 where it says GEN, and within section 2, so you'll pass that Gen tab, within section 2, turn to page 10. And if you look on the bottom of that page, you should see the load combos that we're using throughout the semester. You'll see they sort of start on page 2-10 and sort of trail off into page 2-11. Does everybody who has a manual, you all see that? Everybody go along with that? All right. Let's see. See, again, bring your manual. If you have it, bring your manual. Okay. Now, so if you look, you'll see these load combos that we're using. We're going to be using these load combos throughout the semester. So this is a good section in the manual to place a tab. If you'll notice, I've got a little tab right here on the page, and the tab reads load combos. So if I'm having a hard time remembering what the load combos are, I've got a tab that goes right here. I mean, we're sitting here, I mean, this is the first time opening the manual, and I'm sure some of you are like, okay, now what page am I going to? See, I don't have to do that. All I have to do is, there we go. I'm right there. All right? Saves plenty of time on homework and on celebrations of learning. All right? Sound good? Okay. All right. So you'll definitely want to tab that sheet. Okay. Let's talk a little bit about some basic properties of structural steel, some things about dimensions, things about material values, because this is going to be pretty important, not just today, but throughout the semester. Okay. First off, I have to believe that everybody in this room has seen a picture that looks something like this in one form or another. Am I correct? Yeah. Okay. All right. So this is a stress-strain curve, and this is particularly the stress-strain curve for mild carbon structural steel. A few key points to keep in mind. So first off, anybody remember what we call the slope of this range right here? Young's modulus for the modulus of elasticity. Anybody remember what the Young's modulus of elasticity for steel is? 29,000 KSI. It was always 29,000 KSI for every grade of steel. We're going to be dealing with varying grades of steel in this class, things like A36 steel, A572 grade 50, A992, and what have you. And every one of those grades is going to incorporate the same E. E is 29,000 KSI. Okay? So we have a linear range in our stress-strain curve until we hit our yield stress Fy. Okay? Now this is going to change depending upon the grade of steel that we use. For instance, for A36 steel, the yield stress is going to be 36 KSI, but for A992, it's going to be 50 KSI. So as long as you're able to find that, and we'll discuss where you find that here in a second, you'll just make sure you need to use the appropriate value. So you've got this perfectly plastic region, then you start beginning strain hardening, and you keep increasing your stress until you hit the ultimate tensile stress. We call that F sub U. Okay, so for A992 steel, for instance, the yield stress is 50 KSI, but the tensile stress is 65 KSI. And different stresses are used for different member checks that we'll use throughout the semester. All right. Everybody okay with this basic info? Everybody good? All right. This is just sort of a zoomed in view of right in here. And this is just sort of trying to illustrate the point that you know what happens when you breach or cross that yielding threshold. What happens when you unload the section? You have permanent deformation. And remember, that permanent deformation or that unloading phase always occurs at the same modulus of elasticity. All right. Regardless of whether you learn that in CE materials or you learn that in mechanics of materials, it's the same fact. Right. Sound good? Yes, sir.
Okay, so would it be fair to say when you're designing, is there like a certain section on your yield level that you want to stay in? Picking size wise, so like your level of loading that would be placed on the thing.
Well,
You don't want to get into permanent deformation. So you want to obviously stay on the left side of that.
That's a good question. It depends on what we're talking about. In some instances, we say a little bit of yielding isn't that much of a concern. For instance, when we're designing a member that's subjected to tension, a member that's just being yanked upon, well, in the main body of the member, we want to limit that stress to Fy. But if we look right there around the connection, you're right, in that tight geometry right around the bolts, we say, well, if the stress goes up to past Fy, we're going to get a little bit of permanent deformation. But because the region is so small, we say that's no big deal. Okay. And in some instances, for instance, if we're looking at bolted connections or things like that, our limits for design are based off of the ultimate stress. But one other point I will add to that is dependent upon the type of check, remember we also adjust these by a resistance factor, by a phi value. So this is not always the case, but here's an idea. So when we're looking at limit states associated with yielding, we usually use a resistance factor of around 0.9. But if we look at fracture, we usually use resistance factors of around 0.75. So the idea is that, okay, if we're going to talk about fracture, because fracture is a more, I guess, dangerous failure, if it yields, yeah, it sucks, but all that means is it's just getting a little long. If it fractures, that means we've got some problems. So because we're talking about fracture, we take that usable capacity and actually drop it down lower. Does that make sense? Does that make sense to everybody else? This is good stuff, so I really want to make sure this makes sense. Any other questions? It's good stuff. All right. Okay, so these properties will remain true regardless of whatever steel you're looking at, that the E is 29,000 KSI and that the unit weight is 490 pounds per cubic foot. Now, what will change is Fy and Fu, the yield stress and the tensile stress. That's going to change dependent upon the grade of steel you're investigating. So where do you find that? That's where the manual comes into play. Here's another tab for you. All right, so in that same section, if you, in section 2, turn ahead a little bit to page 2-48, and you should have a table that looks something like this. You should have a grid and a series of squares that are either white, gray, or blackened. Does everybody see that? Everybody kind of see that? Okay. All right, this is a section you're going to want to tab. You will refer to this section quite a bit throughout the semester. It's page 2-48. It should look something like this. Okay. Everybody see that over here? Okay. Now, what this is it lists the Fy and the Fu values for varying grades of steel, but it also lists the grade applicability for different shapes. For instance, to give you kind of an idea, so we have a varying degree of shape we use in steel design. So for instance, we use angles, we use channels, we use HP sections, which are piles, we use wide flange shapes, and what have you. For instance, if I'm using a channel, so let's say I've got a C shape, a channel that I'm using for some particular element. By and large, when I purchase that channel or I use that channel for design and I want to find one for a given, let's say, bracing element, I'm probably going to find that channel in grade A36 steel. That's the most commonly used steel for a channel. So for channels and let's say angles, we're probably going to use A36. If I'm using a pile that's an HP shape, that would be A572 grade 50. That's what those sort of darkened squares mean. The gray squares are, you can find those shapes in that grade if you want, but more often than not, you're going to find them in the black shapes. The white squares mean that the grade isn't applicable. Does that make sense? That'll be, if that's a little fuzzy, I think that'll be a little clear as we start getting into examples and start investigating them. So for those of you who have a manual, let me ask you this. If you're using a W shape, what grade of steel is that primarily going to be in? A992, okay? So everybody with the manual see that? So the reason why you can't see it on the slide is because the table is actually a little bit longer, so it's somewhere down there. Okay. Now, let me ask you this. Now, if you look at A36, okay, you have a yield stress of 36 KSI, but for the tensile stress, there's a range, okay? So what that's basically saying is that if I go and I buy a piece of A36 steel, it by and large should exhibit a yield stress of 36 KSI, but its ultimate tensile stress could be anywhere from 58 to 80, okay? Now, you're the designer. What value do you use? 58, okay? You don't use the average, and you don't use the larger value. You use the smallest value, okay? Because think, that angle or that channel that you're designing 836 steel might be holding up a bridge that your grandma's going to drive on every day. And if you don't want anything to happen to grandma, you're going to assume the worst case scenario. And the worst case scenario is, well, what can I hang my hat on? Can I hang my hat on the 80? Not really. It might be 58. I can hang my hat on the 58. I know it's at least going to be 58, if not more. Okay? Does that make sense? Sound reasonable? Everybody okay with that? All right. Okay. Let's talk about the different shapes that we use. So, you know, we tend to produce hot rolled steel in two main fashions. We're either rolling plates or bars or something like that. And we can then take those plates and then create, you know, plate girders, different box girders and fabricated elements and whatnot. That takes a little bit more welding and a little bit more fabrication time, but depending upon the application, sometimes that's the most economical option. For instance, if you're designing, you know, the bridge crossing or carrying traffic from Nitro to St. Albans, you know, you've seen that bridge, those girders are about 12 foot deep. Okay? Now, on those girders, you can't find that shape rolled at a mill. You have to actually take plates and weld them together to create that I shape, because it's really the only feasible option. But if you're talking about regular old floor beams in a building such as this one, you might go with something like a W shape. We don't call them I-beams anymore because of the different variations that we can produce in this I shape. By and large, the most common, I guess, I shape that we use is a W shape, and the W stands for the fact that we have wide flanges, okay? So a little bit on terminology. When I look at an I shape, when I refer to the flange, I'm referring to this top and bottom flat portion. The inside portion I'm terming the web, okay? Make sense? All right, so a couple other shapes. We have T shapes that we can use, which are essentially cut from W shapes and the like. We have channels that we can use. We have angles that we can use, what have you. When I'm talking about angles, each side of the angle is a leg. Now, I hope by this image, you know, this part is a leg. Right. All right. Sound good? Okay. All right. If you want to start finding dimensions of these shapes, you're going to go, obviously, to the manual. And I've got here this sort of generic tab that just says Part 1. And I'll show you what I have on my manual. And you all can tab as many of these as you like, but I'll show you what I've done. Does everybody see here on the top, you can see these tabs up here? These tabs are referring to the sections in the spec that are relating to these dimensions. And what I have is a tab that starts right at the beginning of the W shapes, okay? I have a tab that's starting at the beginning of the C shapes, the channels. I have one starting at the beginning of the L shapes, the angles, and then the WTs. Now, I've seen students literally tab every single one, and there's like 20 different sections in here. You're more than welcome to if you want. But by and large, I think this is good enough for government work. And when we get into columns and beams, we're exclusively going to be using W shapes. So you'll definitely, at the very least, want to tab those. But by and large, if you see C shapes and WTs also tabbed, you're good, okay? So sound good? All right, so if you don't have a manual, I'd write that down. Okay. All right. Okay, so we are heavily going to refer to these sections throughout the semester. So you will definitely want to make sure that you're familiar with how they're laid out, where you're finding values, where you're finding info, etc. Now, a couple things I'll point out, okay? I guarantee you I've had students who said, you know, okay, I need T sub F. What the heck is T sub F? Well, T sub F, let's say for a given section, I can look up the value, but if you don't know what it means, that's where this comes into play, okay? This schematic on the top of the page will tell you what all of the values that you're looking up represent. So for instance, T sub F, you can see it right here. T sub F is the thickness of a flange, right? Make sense? Okay, that's point one. Point two is which values do you use, okay? Now, for instance, I could do this for T sub F, but I'll use the highlighted value, so B sub F. B sub F is the width of the flange. In other words, how wide that dimension is right here. Now, if I'm looking at, let's say, a W21 by 93, I've got two values that I find. I have 8.42 and 8 3/8. Why are there two values? What's going on there? Okay, well, the reason why there are two values is because there is a difference between the values that you should hang your hat on for the purposes of design and the values that you should use for detailing. In other words, if I go purchase a 21 by 93 and I break out the tape measure and measure the width of that flange, I'm probably only going to be accurate to what, the 1/8 of an inch or the 1/16 of an inch, something like that. So if I go and actually pull the tape, it's probably going to read something about 8 3/8. Okay, but the value that I should actually be using for design is 8.42. So whenever we're looking at values for calculations in this course, we're going to use the decimal values. The fractional values are really what you would be using if you would, say, break out MicroStation or something like that and start drafting it out. Sound good? Okay, all right. So let's just make sure everybody's clear on that. Okay, last thing, let's make sure we understand what's going on with terminology. When I say a W21 by 93, here's what that means. The W refers to the shape. So W would be a wide flange cross section, or there's C shapes, or M shapes, or S shapes, or what have you. So W shape is the cross section. 21 stands for about how deep it is, and I say about because of the differences between nominal and fractional, depths and whatnot. So this is W21 by 93, but the actual depth comes out to about 21.6. Again, all within that same family of W shapes, so but about 21 inches deep. The 93 stands for how heavy it is. So a W21 by 93 is a W shape that is about 21 inches deep, and it weighs 93 pounds per foot. Okay? So in concrete design, if we're trying to determine a beam self-weight, we have to compute it, right? We have to take the unit weight, we have to multiply it by the area of the cross-section. We could do that here, but we don't have to, because as soon as we look up a W21 by 93, we know it's 93 pounds per foot. We don't have to do any calculations. All right. Sound good? Okay. All right. Before we start breaking into this, any questions? Yes, sir.
Is it just a coincidence that the 93 is also
It is a coincidence. It actually is. It's just a coincidence. It's an interesting one. I don't know that I ever noticed it, but I would say it's a coincidence for this section. You'd be probably hard-pressed to find them on maybe even some of your deeper sections or some of your shallower sections. Okay. I don't know if you'll find that on like the W14 by 800. Which, by the way, if you're ever doing a design problem, the W14 by 800, it will work. It won't be very economical, but it will work. That was a joke. But you think if you've got a 30, 40-story, 50-story building, you might be surprised some of those columns there on the ground floor, they're holding up a lot of load. So they're there for a reason. All right, let's get into tension members. Okay, so the first type of member that steel design, the first type of element that we are going to be analyzing and designing in this course is a tension member. And by tension member, I literally just mean taking an element, an angle, a channel, what have you, and pulling on it. Okay, so you're going to find those obviously in things like trusses. You're going to find them in braces in buildings. So they are used quite a bit. We start with tension members because they're, on the whole, they're fairly easy to design, but there are two things that I think will trip you up throughout this semester, and this is not just true with tension members, but everything. The first is this, actually learning how to navigate and utilize this manual. So I want to start off with a topic that's fairly simple in order to address this. Second thing is, I think you'll find the math that we do in here is pretty simple, and I think you'll find that the ideas that we utilize in here are fairly simple. But I guarantee you, you ask anybody who's taken this class before, what will trip you up, if it's not the manual, are the details. When do you add 1/8 of an inch to this diameter? When do you add a 1/16 of an inch? When do you use this shear lag factor versus that shear lag factor? The little nitty-gritty details are the stuff that trip you up. So I do want to take my time and make sure I'm addressing that. Tension members is really a good place to start because it starts to introduce you to some of these fundamental concepts. Okay. Now, so this is, I'm sitting here, I'm getting ahead of myself. This is the same stuff that I was just saying, that we can find tension members just about anywhere, but it's a very good place to start the class. Okay, so let's talk about how we would basically go about this. If I have a tension member and I'm yanking on it, okay, I have had mechanics of material, mechanics of deformable bodies. So if I take a member and I yank on it, I develop some axial stress, okay? Now the stress I develop is P over A, right? The applied load divided by the area. Remember, secret weapon of structural engineering is a samurai sword or a lightsaber if you're a sci-fi fan, right? Cut section, and then there's a load applied over that area, whatever the area is of the section, you're going to develop some stress. So if we said, all right, I have to limit that stress to some value, to 50 KSI, to 36 KSI, what have you, I could then solve for the load required to reach that stress. So if sigma equals P over A, I can multiply both sides and find that the maximum load is whatever that limiting stress is times whatever area that I'm looking at, whatever the area of the cross-section is. Sound good? That is, by and large, the basic idea of how we handle tension members. Now, we're going to look, when we look at a tension member, we're going to be investigating various different what we call limit states. And a limit state is a condition that we define as, a given point of safety for the structure. So the idea is, if I'm looking at a tension member, a limit state might be something like yielding. So this particular section cannot exceed Fy. If I exceed Fy, I have failed that limit state. Okay? So there's different limit states for yielding, different limit states for fracture, for buckling, for things like that. Okay? So if I introduce that, I want you to understand what's going on with that. Now, we tend to identify two different types of limit states, by and large, in structural engineering. The first one is a strength limit state, which is related to safety. In other words, if we violate that limit state, we're starting to compromise the safety of the structure. Grandma has the potential of falling in the river, and we don't want that to happen. Okay? Make sense? Okay, so that's point one. Point two, or the other type of limit state that we deal with, is what's called a serviceability limit state. So a serviceability limit state, a very common example of that would be something like excessive deflection. There's plenty of instances where a beam has more than enough capacity to hold up the loads that it's subjected to, but the design of that element was governed by ensuring that it doesn't deflect too much. I mean, deflection and failure are not necessarily aligned. If I'm looking at this floor system, above here, that floor, let's take a look at a given beam. We might have a beam that can hold up 200-foot kips of moment, and it's only being subjected to 50. It's certainly not going to fail, but you wouldn't like it if the floor beam was like this, would you? You wouldn't like it if it was sagging, 2 feet. So there are many instances where it's not the strength that matters, but it's the serviceability. Things like deformation, ensuring that we don't have too much vibration in the structure, and things like that. So for most of what we do though, in here, we're going to be dealing with strength limit states. Okay, so let's look at a tension member. So I have here some wide flange shape. You can think of it as an I-beam, but again, we don't use I-beams, that particular term anymore. Looking at a wide flange shape, and I'm taking, let's again be clear, I'm taking this wide flange shape and I'm yanking on it, okay? Now, I'm going to define and discuss its pertinent limit states, the limit states that matter, okay? Now, before I get into that, one thing to note, see what I've got right here? I've got bolt holes, right, for a bolted connection. So that particular area is going to matter quite a bit to us. All right, Now, the first limit state we're going to look at is what's called yielding in the gross section. And basically, we're just going to try and ensure that the main body of the member, when I refer to the gross section, I'm talking about just the main body of the member. So I got a connection here and a connection here. But everywhere in between, we're calling that the gross section. And I'm just going to try and ensure that the gross section of the member does not incur excessive yielding. I got a few videos just to make sure everybody's awake and give you kind of an idea of what's going on. So this is a video of a tension member incurring yielding. This one's a little boring, but I think you'll get an idea of what's going on. So I'll mute that. So we have a piece of steel being banked on. You can kind of see if you pay attention to the grid, it's starting to along. You can see it's still going, and there it goes. Okay, so this would be an example of yielding. The idea it just starts to incur that excessive permanent deformation. Okay, now going back to that original idea I brought up earlier, so we have a member, it's got some load P, it's got some cross-sectional area A. We can determine the maximum load as stress times area. Make sense? So what we do for yielding in the gross section is we define the nominal capacity as Fy times the gross area. Okay? Now, if we refer to the steel construction manual, what that means is I want everybody to find this. Okay, so let's look at a couple things. So this equation can be found on 16.1-26. I want to take a little bit of time and investigate this. Okay, so for those of you that have your manual, I want you to look at this. Okay, you see this gray section of the manual right here? I want you to turn to this bulk before that, like about right here. Okay, everybody see that? Somewhere about right here. You'll notice if you turn to that, you're probably going to be in some sections that'll be listed, like B4 or C2 or C3, something like that. Does everybody see that? I want you to go to that section and I want you to turn to Chapter D. Okay? You'll see, if you look on the top, your pages should say something like 16.1. It'll start on 16.1-26. Okay? So I want everybody to find 16.1-26. Okay? All right. Now, what is the title of Chapter D? Design of members for tension. So it sounds like we're in the right chapter, right? Sound good? Okay, now, let me explain a couple things about the anatomy of this document. So right now, we're in Chapter D, Design of Members for Tension. If we go to this gray section in the back, if this is the code, the gray section is the commentary, okay? Now, for every chapter in the code, there's a corresponding chapter in the commentary. So the idea is I might go to Chapter D and it might give me some equation. If I want to know where that equation came from, I would then refer to the commentary, and the commentary would explain, okay, that stuff that you looked at in Chapter D, here's why it's there, okay? So the commentary will help explain what's going on. And a lot of, or I'd say a lot of, virtually all structural engineering specifications will be laid out something like that. You'll have code, and then you'll have commentary that goes along with it. So if there's anything that you want to know more about, go to the corresponding section in the commentary. Sound good? Okay. Now, we are in the chapter D, Design of Members for Tension. Each chapter corresponds to a different type of design. So Chapter E is Design of Members for Compression. So that's when we talk about columns. Chapter F is Design of Members for Flexures. That's when we talk about beams. Okay. So various chapters have, obviously have various purposes. We're in Chapter D, Design of Members for Tension. We go to the very bottom, Section D.2, Tensile Strength. And I'm going to read this out, and you all can follow along with me. So I'm on 16.126. Tensile strength. The design tensile strength, VPN, and the allowable tensile strength, we're going to ignore that since we're not using ASD, we're only using LRFD. The design tensile strength of tension members shall be the lower value obtained according to the limit states of tensile yielding in the gross section and tensile rupture in the net section. So for tensile yielding in the gross section, we use equation D2-1 on page 16.1-26. And the equation is the yield stress times the area of the section, or in other words, the gross area. Okay? Does that make sense? Everybody okay with that? All right. Notice how it lists the phi value associated, the phi value of 0.9. Okay. Everybody good? Yes, sir.
For fabricated members, like the really deep ones that you're talking about, I mean, those will be in the steel manual. How do you produce those values?
Talk about the gross area and things like that.
Yeah, whatever else is in there.
Stuff like that you would just have to compute. So instead of having the tables listed for you, you have to go through and actually compute them. You have to say, okay, what is the area of this plate? What is the area of that plate? And start to add it up. When you get into that realm, I'll say this, Excel becomes your best friend, because you can write an Excel spreadsheet that, given a top flange dimension, a web dimension, and a bottom flange dimension, will compute all those necessary properties for you. And there's stuff out there that you can find, but when you get into the world of customized steel design, plate girders and things like that, it in fact becomes very custom. So you have to sort of roll up your sleeves and do all the math yourself. And that's sort of the nature of the beast when you get into that world. The same thing's arguably true in a lot of things in concrete design as well. It's just is what it is. It's just the difference between using pre-canned solutions, like precast elements or wide flange shapes, versus using custom solutions. And custom solutions, the advantage is that you have more flexibility as the designer to tailor the reinforcement and sizes and things like that to your appropriate demand. The downside is you have more math to do. But that's what we pay engineers to do, is do more math. So, sound good? That answer your question? Everybody good? All right, we'll talk about some of that stuff in concrete design as well. Okay. Now that's the yielding state according to gross section yielding. The next one is net section fracture. So the gross area is the main body of the member. The net section is right there around the connection. Now, what we are worried about in the net section is not yielding, but fracture. And I think you can probably see where this is going. Here's what net section fracture looks like. So I've got a video looking at something very similar. You could go to those YouTube links if you want. This is just the same videos from those YouTube links. But we have a section that's being subjected to tension, and we're investigating not the main body of the member, but right there around the connection. And you can see what's going to happen. You can even kind of visually see a lot of the yielding on it. There we go. Okay. So around the connection, we're a little more concerned with fracture than we are yielding. I mean, we allow a little bit of yielding right there around the connection, but let me pause this. But really what we're more concerned about is fracture. So it's the same idea. It's still a limiting stress times an area. The area is a little different, okay? The limiting stress we're going to use is not the yield stress, but it's the tensile stress, so F sub U. The area is the effective net area, A sub E. We'll talk about that. I'd say by and large, throughout this section on tension members, the thing you're probably going to have the most trouble with throughout all of this is the effective net area. So that's the stuff you're really going to want to pay attention to. But yeah, so F sub U times the limiting area. We have a resistance factor. It's a little lower because this is a more, I guess, catastrophic limit state. But again, if you go back to the spec, it's right there. For tensile rupture in the net section, FUAE, and our phi value is 0.75. Sound good? Now to compute that effective net area, we're going to spend quite a bit of time discussing exactly how you do this. But by and large, you take the net area, the actual area right there around the connection, and you then adjust that by what's called a shear lag factor. And don't worry, we're going to discuss shear lag and that effect in very great detail later. So I'm throwing a bunch of equations at you, but we really are going to dissect them one at a time and take our time with this. The last one that I do want to mention is something that we'll address at the very end. This one's a little strange, but it's called block shear rupture. It's actually discovered by accident. They were doing some lab testing on some connections, and then this sort of happened, and they went, oh, well, I guess we need to account for this. But the idea behind block shear rupture is you get sort of a combination of tensile failure along one path and then shear failure along another path, and you kind of rip a chunk out of the connection. So let me kind of show you how this works. So this is a block shear failure. Now it's sped up a little bit, but you can kind of see. So here we got, does everybody kind of see how we've got an angle that's being loaded? Now, what's going to happen is we're going to develop a failure that's sort of a tensile failure along this path and a shear failure along this path, and this entire chunk is going to kind of be ripped out. So you can kind of see it's going, and whoop, and there we go. Now, I do want to show you something real quick. Now, I want you to pay attention to what the angle looks like during its loading conditions. I'm going to press play, but didn't it kind of look like as you were loading this angle that it wasn't really being loaded evenly? Like this section of the angle was kind of seeing more load than this section. Did everybody kind of see that? Like if I go ahead and press play, everybody kind of see how that's going on? How there's an uneven loading? There's a name for that uneven loading effect in tension members, and we call it shear lag. So that's what I'm talking about in terms of shear lag. We will get into that throughout the throughout our discussion with tension members. What I'm going to do for today, since we're getting close to time, is I'm going to go ahead and stop it. We are going to take our time with tension members, but the first task that we have to address, and the first thing we need to discuss, is how exactly do we compute some of these properties, specifically gross area and net area. We'll take those first, then we'll address shear lag, and it's funny how we'll start analyzing and ultimately designing tension members. Sound good? All right, that's all I've got for you for today. We will pick this tension member discussion up next time. That's all I got.